Section 4 of this unit is talking about some specific triangle relationships. So we're going to talk about the bisector theorem, some angle side relationship, and the triangle inequality theorem. So as we learned in section 3, a perpendicular bisector just by itself is something that was perpendicular and bisected, but we didn't have anything going on up there, so it was only useful on this side. But when we get to the perpendicular bisector, some unique things are going to fall in place, and then some interesting properties and results are going to happen. So if a point is on the perpendicular bisector, so this is what we have to know. We have to know we have a perpendicular bisector, and we have to know we have a point on the perpendicular bisector. So two pieces of information. So if we look at this blue thing first, here, we'll focus here first. So we would know that this is perpendicular. We would know that information. This is on, D is on. What we get as a result are these two things. We get its equidistance from the endpoints of the segment. So in our example, we get GD equals ED, and it bisects the angle. And so then we get that angle GDF is equal to angle EDF. So pretty powerful theorem if you know this, because you get two extremely useful pieces of information. There's also some relationships between angles and sides in triangles. So if one side of a triangle is longer than another side, then the angle opposite the longer side has a greater measure than the angle opposite the shorter side. If one angle of a triangle has a greater measure than another, then the side opposite the angle is longer than the side opposite the lesser angle. These two are really converses of each other, and I think it boils down to this. So this one, big side, points at the big angle. Little side, little angle. Part B is just a reverse. If you have big angle, it points at the big side. So what this allows us to do is match up or order angles greater to lesser, lesser to greater, angle sides from least to greatest, greatest to least. Because you have to, physically, if you have the biggest angle, it has to be opposite the biggest side. And similarly, littlest, or the littlest, has to be opposite, this is probably the littlest side here. So let's look at an example. Order the lengths of ABC from smallest to largest. Well, you first may think, well, I don't know A, but remember, triangle sum, I can find out that A is 85 by taking 180 minus 65 minus 30, and now biggest angle, biggest side. Now naming convention, capital A in a triangle, the side opposite is little a. Capital B, the side opposite is little b. Capital C, the side opposite is little c. That is the official math notation, so that we're all talking about the same side A, same side B in relation to angle A and to angle B. So smallest to largest. So A is the largest. We'll put that one at the end. 65 is in the middle with C. And our littlest one is 30. So littlest, 30, is opposite B, 65 and C and A and 85. So this is least to greatest for the sides. If we look at the next example, and we order the angles from smallest to largest, here's my smallest side. It goes to the smallest angle, so that means angle C. So from 4 we go to 5. 5 is opposite B. so that's the next biggest, and our biggest side is 6, so our biggest angle is A, because they're opposite each other. Another thing that we can know about triangles is whether or not a triangle can even be formed. You can't make a triangle with just any 3 lengths. There are some rules, and this is the criteria. You must meet all 3. So in words, it's the sum of any 2 sides must be greater than the third side. And all of these must be true. If any one is false, the triangle cannot be formed. So let's look at a couple of problems that would come from this theorem. Can 2, 3, and 5? 2, 3, and 5. Well, let's run the equation. So 3 plus 5, is that greater than 2? Is 5 plus 2 greater than 3? And is 2 plus 3 greater than 5? So I went through all of the situations, 2 sides greater than the third. And then we have to go through and say, well, 3 plus 5, that's 8 greater than 2. That's true. 7 is greater than 3. That's true. 5 is equal to 5, not greater. This is false. Therefore, no triangle. You cannot make one because this one right here is false. Equal is not the same as greater than. So how about 5, 7, and 9? So 5 plus 7, is that greater than 9? Is 7 plus 9 greater than 5? And is 9 plus 5 greater than 7? If you need a picture, go ahead and draw it. First one is true. 16 is greater than 5. True. 14 is greater than 7. True. Therefore, yes, it can make a triangle. Now the other thing we could do is we could find a missing length. And instead of finding a missing length, we're going to find a range of values, a minimum and a maximum. So if you're building a garden and 2 of your sides are dictated, how big or small could that third side be? So I set up my 3 relationships. 4 plus s has to be bigger than 7. 7 plus s has to be bigger than 4. And 4 plus 7 has to be bigger than s. So those are the 3 relationships from the theorem. So if I subtract 4 from both sides, s has to be bigger than 3. If I subtract 7 from both sides, s has to be bigger than negative 3, and 11 is greater than s. For fun, let's just flip that over. Really means s is less than 11. S is bigger than 3, that's my bottom. It has to be something bigger than 3. Can't be 3, it could be 3.00001. A negative number doesn't make sense when we're talking about length, so I can discount that. And S has to be something less than 11. It can't be 11, but it could be 10.999. So there are your range. It's kind of nice to write it this way, that S has to be somewhere between 3 and 11. So go ahead and try the check problems and then tune in for the next set of videos.